Hi!
Hey guys!
My best Maley impersonation for you
Hey
folks.
guys!
Guys, we're on page 107. I know it's been a while since you saw me. It's great. I'm back. Special case equations. Here we go. So we just saw examples 1, 2, and 3. Right? We now learned that sometimes our equations don't always have one answer. Sometimes they might not have an answer. No solution. Sometimes they might have an infinite number of solutions, right? Meaning any number we can think of, right, to replace our variable with will work. Okay? So we're going to keep going with that. We're going to solve some stuff. We're going to talk a little bit about some of this stuff. Are you guys ready for the fun?
Yes!
I think we are. All right. Will a one variable equation always have only one solution? Right? Well, I just said it a second ago, but in case you weren't listening, because nobody listens to me anyway, the answer to that, of course, is no, right? So sometimes we can have, and here we go, guys. We can have one solution, right? That's what has happened in 2-1 and 2-2 and 2-3, right? We got one answer. Now we learned today, sometimes we will not have an answer. We will have no solution, okay? And then the third option, again, also learned from today, is that we have an infinite number of solutions, okay? You will, hold on, grammatical mistake. There we go, infinite solutions. You will learn, I do not write infinite, I just put INF. Mr. Noel writes out infinitely many solutions. He's better than me, folks, okay? That's why. All right, so there we go. In order for us to figure out, do our equations have more than one solution or no solutions, we got to do a little bit of solving and then a little bit of looking and understanding, okay? All right, here we go. We can move down here to number 2. Make my pretty handwriting go away. All right. Kaylee, what you up to? She writes this equation right here. Can you find the number of solutions this equation has without solving for x? The answer to that, guys, is yes, we can, right? But we really have to understand and know what we're looking for, right? We have to really know what we're looking for. So the very first thing I want to do, distributive property on the right-hand side. So we are going to leave 6x plus 12 alone. And this is going to turn into 6x plus 12, okay? All right. So here's what we need to do. If I don't want to solve for x, we can stop right here and look at variable term. Hopefully you all know what I mean when I say look at the variable term, okay? All right. If they are identical, are those identical? Very hard to see with purple, Mr. Noel. Very hard to see.
Yes, but they are identical. It won't go.
It won't go. Here, we'll make it even worse. Okay. All right. If they are identical, right? If they are identical.
Which means the same.
Right? Which means they have the same variable, duh. But more importantly, guys, the same coefficient. Okay? Positive 6. Positive 6. When this happens, lights and sirens and horns should be flashing, going off in your head. A special case equation is about to happen. Okay?
I love these.
Okay? When this happens, right? So look at the variable term. If they are identical, right, this means special case. Okay? If this doesn't happen, right? Okay? If they are identical, there's thing number 1 that could happen, right? What's the other thing that could happen, folks? Well, they're either going to be identical or they're not going to be identical, okay? So if they are different, this is what we know all of our equations to be, right? 1, I'm writing over here because I'm going to use that space over there. 1 solution, okay? If they're different. So if you have 5x and negative 22x, are those different? 1 answer. If you have 5x over here and 5x over here, special case, okay? So then it's going to be no solutions or one solution, depending upon what kind of numbers you have, folks. We'll try to be a highlighter. No, we're not going to be a highlighter. We are going to put boxes around. Once you identify that your variable terms are identical, right? I had 6x here. I also had 6x over here. That tells you it's a special case. Then you just look at your numbers. Are these numbers identical? If they are, then that means here, we're going to go up, right? So if they are the same, actually here, hold on. This is like a weird flow chart. If these are the same, then
we're going all over the place.
Then you have infinite solutions. Okay? All right. Now, if my numbers weren't the same, say this was 12, but this was like 18, then they're different, right? So if my numbers are different, that's our other special case, guys. That is no solution. Good luck reading that with that writing. That came out okay. Okay?
Yeah.
A lot going on here. We'll probably give you a handy flow chart that shows all this in here so that you can get used to using it just like we did with our flip and fold notes and everything else. But anyway, guys, that's how we don't have to solve an equation, but we can kind of learn through the structure of it how many solutions it will have. Okay? Okay. That was a lot of talking. I just want to solve some stuff, guys. I'm not even going to worry about 3. We're going to bebop right over here. How many solutions does the equation have? All right, so we got to do some combining like terms, distributive property first. I realize you can't see that as well, so let me zoom in a little bit more. Does that look good for you folks?
Yep.
All right, here we go, multiplying this in here. So 3 is going to get distributed into both of these. What is that, 7.2?
7 and 2/10.
Okay. On the right-hand side,
there is no distributing, but we do have like terms.
I do have like terms, so we're going to go ahead and combine those together right now. Ooh, sorry, folks. There we go.
Terrible box.
Rectangle now. Okay, combine those like terms. 4.1x plus that is also 7.2x plus 7. Okay, we're going to use what we just talked about a second ago. Look back over here on what we wrote on number 2. Okay, so I want you to look very closely.
Coefficients, those look to be the same.
Are those the same or different? They are the same, right? That means special case. Okay, now we have to look at our numbers, right? So the coefficients tell me it's a special case. Now we look at 12 and 7. Are those the same or are they different? Those are different, right? So because our coefficients are the same, but our numbers are different, guys, no solution. Okay?
So you're telling me there's no answer to that, really, right?
Nope.
That's kind of, what?
Mm-hmm.
Not even you can solve it?
I can solve anything. But that one, we can solve it. It doesn't have an answer. Guys, we won't use our flow chart. We're going to solve number 5 the old-fashioned way, like we've been doing, and let's see what happens, okay? All right. Let's say we don't recognize any of that stuff, right? I don't realize that I have the same coefficients in my variable terms, right? I go, oh, yeah, I got to combine these right here. That turns into 10x,
10x.
minus 8, right? This turns into distributive property. Okay, this is 10x minus 8. Okay, I need to move my variable terms over. So I'm going to move this 10 over here, right? Here we go. We're going to move this over. So, yeah, subtract it, okay? And go ahead and subtract it here. Okay, yep. This cancels out, goes away. All I have is negative 8. Uh-oh. Right, we've seen this happen on some of our equations. When our numbers go out, we get 0. Well, guys, that's okay. This cancels out as well. Once again, folks, when your variable cancels out, this should be a time where like horns and sirens and buzzers go off in your head and say, wait, this doesn't look right. What's going on? Okay, now we have to make meaning of this. -8 equals -8. Is this a true mathematical sentence equation?
Yes.
Yes, it is, right? Because this is a yes, right? It is true. This is infinitely many solutions. Okay? So, again, folks, if we recognize that we have identical variables, right? Our coefficients were identical here, but we didn't notice it. We can still solve and get the right answer. Or if we notice it, we don't even need to solve. We can just then look at what numbers we have on both sides. Okay? All right, moving on. Todd and Agnes making some oh man, I got no room to write anywhere here, Mr. Knoll. This is all bad.
Desserts. Got a little bit.
Little bit, but not a whole bit.
A little bit.
I need a lot of room. I like to write all over the place, as you saw. Okay. Todd buys peaches and a carton of vanilla yogurt. I think I know what he's making. Agnes buys apples and a jar of honey. Okay. They bought the same number of pieces of fruit. Again, we don't know how many peaches. We don't know how many apples they bought, but they bought the same number. Is there a situation in which they pay the same amount for their purchases? Well, if we look at the picture, Todd's paying $1.25 for his peaches. I don't know how many. Maybe he bought 2, maybe he bought 20, maybe he bought 10. Right? He's going to pay $1.25 for each one per peach. Okay? We start to figure out which is the variable term, which is the constant term when we write these expressions. Remember, in class we talked about when you see that word per, that's usually a dead giveaway. There's your variable term. So when we're talking about each or per peach or per apple, that's a giveaway. That's probably going to be your variable term there. Okay? So we need to set up 2 equations. Guys, I'm going to write them over here. Okay? So we're going to have Todd. We're going to make an expression for him. We're going to have Agnes. We're going to make an expression for her. We're going to set them equal to each other. So we're talking about $1.25 for each piece of fruit. Plus he buys his yogurt for $4. So this is my buddy Todd. Okay. Agnes, on the other hand, spends $1 for an apple. Again, don't know how many apples she bought, but then she also bought some honey. Okay. So there we go. There's what our equation looks like. All they want to know, is there a situation in which they pay the same amount for their purchases, right? So in other words, guys, is there an answer to this? What do you guys think? I don't know. If you don't know, let's keep solving this. Let's see if we can solve it. Okay? I believe that we can. Again, is this a special case equation? Hopefully we're starting to realize no, right? I have different coefficients with my variable terms, right? So my variable will still live on. So we can solve this equation for f, right? So we should get an amount. Let's say you want to know how many pieces of fruit it is. We move this smaller one over. That's 1. I'm left here with, watch this, guys, 0.25f plus 4 equals 6. Okay, 4's got to move over now. We're going to subtract 4 from both sides. Writing down here, 0.25f equals 2. Okay, divide by our coefficient. So we divide by 0.2,
5,
and we should get 8. Right? I believe I did all that right.
Absolutely, you did.
So
what
that
does that
mean?
mean?
That means, yeah. What does that mean? I know what it means. Do you know what it means? I think you just said it. That means when they buy 8 pieces of fruit, they pay the same amount, right? How much is that? Well, it happens to be $14. Okay. Anyway, there we go, guys. There's page 107, right, on our key concepts for lesson 2.